Okay, so today we'll finish redistribution mechanisms, and this is a good point to stop. We'll end all the lectures today with the description of some loose aspects of these redistribution mechanisms. But I will hold at least one more class on clarifying any doubts that you have or discussing something. So we'll have it in another week or so. So in the meanwhile, just collect all your doubts and send it to me, and we'll have one class with that. Okay, so last time where we were, we basically finished this Crampton-Gibbons-Klepper main result, which said that equal partnerships can always be dissolved efficiently, and the set of partnerships that can be dissolved efficiently is a convex subset around the equal partnership. So for the uniform distribution, when values are drawn using a uniform distribution, and with support 0, 1, the set of partnerships that can be dissolved for 3 agents look something like this in the figure. So the equal partnership is at the centroid of the simplex, and these are all the red areas are all the partnerships that can be dissolved. And as there is, one of the other corollaries that we saw is that one cell or many wire partnership cannot be dissolved efficiently. So this is independent of what distribution it is. So these extreme points of the simplex are not, cannot be dissolved efficiently. So the natural question is like, what is this result telling us? It's first, it is a remarkable result because it clearly spells out what kind of property rights can be dissolved efficiently if it comes to dissolving it. Okay. The second aspect is the intention of the model is to keep information symmetric. So all the agents are drawn from the same distribution with the same support. And so the agents are symmetric ex ante informationally, but the property rights are different. So the only driver for the results in this model is basically asymmetric property rights. It's possible that in many settings, not only are the property rights asymmetric, but there are agents who draw from different distributions, and so agents are also asymmetric ex ante. So what happens in that case? Well, the results are no longer cleaner as in the symmetric case. So it will depend on how this information asymmetry and property rights asymmetry work out. Uh, so this paper by Figuera and Scretta, they analyze that setting, and basically they show that equal partnerships may no longer be dissolvable. Okay, so the figure may look very different than this if the agents are not symmetric. Okay. There are some other papers which extend this theory and so on. Okay, so that's where we had stopped. So today what I want to look at is, because these mechanisms are basically quite complicated to describe and discuss. So we saw the mechanism in the paper, in the proof of the main result is quite complicated. The paper has some slightly, simpler mechanisms, but in any case, the solution concept used is Bayesian incentive compatibility. So the question is, are there dominant strategy mechanisms which can also do the same job? Well, the short answer, as we will see through an example or one particular model, is that it's not possible. So as is the case in many settings, a dominant strategy incentive compatibility is too strong a solution concept here. Okay. So that's what I want to explore today, that why is dominant strategy a big, and how is dominant strategy a big obstacle in achieving redistribution, and what are some of the ways around it, and so on. Any questions? Okay. Okay, so what we will start off by studying is a very simple trading model where there are just two agents, a buyer and a seller. So we'll call them B and S. And basically, we are going to explore if a dominant strategy mechanism exists in this model, which is efficient and budget balanced. Okay. So we're going to assume that values of both the agents are distributed between, let's say, 0 to 1. So, you know, it's not required that we consider 0 to beta. Let's consider 0 to 1, some distribution of values. The distribution won't matter in this case because everything will be prior free, except for the fact that these values are in this interval 0 beta. Okay, so consider any DSIC efficient and budget balance mechanism. So notice that I'm not imposing any individual rationality constraint. I'm just looking at a mechanism which is DSIC efficient and budget balance. Okay, and let's say that the net utilities that both the agents are getting is UB and US in this mechanism. So net utility is what is the utility that you know. So there is a typo here. This would be 0 beta square, and this also 0 beta square. Okay, so so this net utility is an exposed utility function, which is basically if the buyer has type VB and the seller has type VS, then what is the utility of the buyer from the mechanism? Well, it will be VB times the probability with which the mechanism awards the object minus the minus the payment the buyer has to make to the seller. Okay, so that's basically it. So in this case, of course, the allocation probabilities are very easy to compute because we are using efficiency. So efficiency will require that if buyer's value is greater than seller's value, then the buyer should get the object. Otherwise, the seller should get the object. If VB is equal to VS, we may do whatever we want. It won't matter. But at least when VB is strictly greater than VS, B gets the object. If VS is strictly greater than VB, then S should get the object. That's what efficiency means. Okay. Uh, Budget balance means that the total payment in the mechanism is 0. So whatever the buyer pays, the seller receives. There is nobody else to pump money into the system or take money out of the system. So the buyer's payment and seller's payment must cancel each other out. A consequence of that is that because the payments are canceling each other out, when we add the payoffs of or the utilities of both the agents, what we will be left with is only the buyer value times the probability of buyer winning plus the seller value times the probability seller winning. Okay, and because it's efficient, what it will boil down to is that if VB is greater than VS, it's going to be equal to VP. Otherwise, it's going to be VS. Okay, so this basically means that a budget balance and efficient mechanism redistributes entire surplus, and if VB is greater than VS, then basically that surplus is VB, otherwise the surplus is VS. So any questions so far on this slide?
No, sir.
Okay. So we know that if there is a DSIC efficient and budget balance mechanism, then it will have this feature that UB plus US is equal to VP if VB is greater than VS, otherwise it's equal to VS. So far I have just used budget balance and efficiency. We know that the mechanism is dominant strategy incentive compatible. So we can use some version of this payoff equivalence formula. Okay. So the payoff equivalence formula, just to remind you, it says that in the dominant strategy case, fixing the type of the other agent, okay, the net utility of an agent is equal to the net utility of that agent at the lowest type plus the integral from the lowest type to the actual type, uh, the allocation probability. Okay, so in other words, this follows because the derivative of the utility function or the subgradient of the utility function is equal to the allocation probabilities, and so we can write it like this from the fundamental theorem of calculus. So here, because of DSIC, we can use this payoff equivalence formula. So remember, a mechanism is DSIC if and only if allocation rule is non-decreasing and this payoff equivalence formula holds. So in our case, because the allocation rule is already efficient, it is non-decreasing, so that automatically is satisfied, and so this also must hold. So in particular, I look at a type profile, VB VS, such that VB is greater than VS. So in this case, efficiency means that the buyer should get the object. So trade happens at this profile. And what we see is that UB, VB, VS, the utility of buyer at this type profile is equal to UB0 VS plus the integral from 0 to VB QB x Vs dx. So this is the allocation probability of the buyer at x given that the seller has type Vs. Okay, so this this can be simplified because this, remember, this is the efficient allocation rule. So this is equal to 1 as long as x is greater than equal to Vs, right? Otherwise it's equal to 0. So this integral just boils down to VB minus Vs. Okay, so we get UB VB Vs is equal to UB0 Vs plus VB minus Vs. Okay, so far I have just used that Q is efficient and this payoff equivalence formula to get this. Now in this step, I'm going to use that this is a budget balance mechanism. So remember what I said here, that the sum of payoffs is equal to the surplus generated. Well, what is the surplus generated here? If the buyer's type is 0 and the seller's type is VS, then in such profiles, the seller will keep the object and the surplus generated will be VS. So UB0 VS plus US0 VS is equal to VS. So in other words, I can write UB0 VS is equal to VS minus US0 VS. Okay, and this I keep as it is. Okay, now I just I use the payoff equivalence formula one more time, but this time with the seller. Okay, so remember US0 VS is equal to US00 plus the integral from 0 to VS US Q of 0 Y dy. Okay, but the allocation probability is all going to be it's so if the because the buyer's value is 0, the seller will always get the object at all those profiles, so that integral will come out to be again Vs. So what you will get is that Vs minus US0 Vs is equal to minus US00. Okay, so these two terms will be equal to minus US00. Okay. So this, the way to look at it, just that, if you have a piece of paper or something, you can just write down that US0 VS is equal to that integral formula, and you'll immediately get that this is equal to this because of efficiency. Okay. And so this term is replaced by this, and this is here. So all we wanted to do here is that we wanted to write payoff or utility of a buyer at a particular profile as a function of the payoff at the lowest possible uh, uh, profile, which is 0, 0. And so we wrote it like this. So this is a simplification we have done to this using payoff equivalence formula. So
Sir,
what
is there any interpretation of the last equality?
So there's not no interpretation at this point. So all I'm saying is that I'm going to use these manipulations to get to a contradiction. So I'm going to show that such a mechanism can never exist. Okay, so that's what I'm going to show. So at this point, I'm just saying that if such a mechanism existed, then we will have to satisfy all these payoff equivalence formula, and we can use budget balance and efficiency to simplify these payoff equivalence formulas, and that basically leads us that this is equal to this. But then we can use an identical argument. So this I did for the utility of the buyer. I can do a similar thing for the utility of the seller. Okay, so what is US of VBVS? Well, again, it's equal to US of VB0, so the lowest type of the seller, plus the integral from 0 to VS QS VBX dx. Okay, and because the VB is always greater than VS, at all these types, the seller will never be allocated the object. So this is always 0 at any VBX, where X is between 0 and VS. So as a result, this term just disappears, and we just have US VB0, which is equal to using budget balance, VB minus UB VB0. Remember, the buyer's payoff plus the seller's payoff is equal to the surplus, which in this case is VB. So we get this from algebraic manipulation, and then basically uh, so the last step will again use the payoff equivalence formula for the buyer now. So if you use the payoff, if you expand UB VB0 equal to UB00 plus that integral, then you will get that this is equal to this. Okay, so we,
Excuse me, so
yeah.
in the first expression, how is the second term equal to 0?
Well, efficiency says that uh, if the buyer's type is more than the seller's type, then the buyer should get the object. So if since we have to start with, uh, so we have assumed that VB is greater than VS, and so VB is greater than X also, because X is between 0 and 0.
Okay, got it.
Particular type profile, the buyer will get the object and the seller won't get the object.
Okay, sir.
So we get this. So that means that, at this type profile where VB is greater than VS, we can use this fact that UB plus US is equal to VB, because VB is greater than VS. So if you use that, so VB is equal to UB plus US, but UB is this and US is this. So if you substitute, then we get VB minus VS minus US 00 minus UB 00. But US 00 plus UB 00 is equal to 0, again because of budget balance and efficiency. So this is equal to VB minus VS. this is a contradiction as long as Vs is greater than 0. Okay, so we can never satisfy this, this kind of payoff equivalence and DSIC, budget balance, and efficiency in these kind of environments. Because if we satisfy, then for some VB greater than Vs greater than 0 at such profiles, we immediately get a contradiction. Right, so that's what is well known as the Green-Lafont impossibility theorem. That in the bilateral trading problem, at least, there is no DSIC efficient and budget balance mechanism. Okay, so notice that there is no participation constraint required for this impossibility. Only incentive compatibility, efficiency, and budget balance are incompatible. Okay. So contrast this to the mechanism that we had for the, we saw in the proof of the Crampton-Gibbons-Klemperer result. We constructed this mechanism. This is the transfer rule, and the Q was the efficient rule. We showed that this mechanism is indeed budget balanced, Bayesian incentive compatible, and by definition efficient. uh, it satisfied the individual rationality when this condition is satisfied, the Crampton-Gibbon-Klemperer. But if I did not have interim individual rationality, that constructed mechanism is always Bayesian incentive compatible, efficient, and budget balance. So what I'm telling you is that if we weaken the incentive compatibility property in this model to BIC, there will be mechanisms which will satisfy BIC efficiency and budget balance. But with DSIC, there is no such mechanism. Okay, so participation is is the problem when we go to BIC. But for the impossibility result with the DSIC, we don't even need the participation constraint. So is everyone clear on what this result is exactly saying?
Yes, sir.
Right. So, for instance, suppose the mechanism designer can force everyone to participate. Okay, so there is no choice of, once you are in the mechanism, you realize that you're going to get negative payoff. So there is no choice of, not participating and going back. So I can force everyone to participate. Okay, so in these kind of environments, we know that a Bayesian incentive compatible, efficient, and budget balance mechanism exists, which is the Crampton-Gibbons-Klemperer mechanism. Okay, at least for single object, that mechanism is well defined. What this result is saying that, well, that is only if you allow for Bayesian incentive compatibility. As soon as you allow for dominant strategy, the solution concept is too strong to allow for such mechanisms. Okay, so any such mechanism must necessarily have this prior heavy solution concept of Bayesian incentive compatibility. You cannot achieve such things in a prior free manner. Okay, of course. So now then you can step back and look at the Crampton-Gibbons-Klemperer paper. So what the Crampton-Gibbons-Klemperer paper is saying that, okay, even though this there is a mechanism which is BIC efficient and budget balance, it can only satisfy individual rationality, interim individual rationality for certain property rights. Okay, it cannot satisfy all the time. Okay, so there you will get a impossibility in the bilateral trading problem where the property right structure is extreme, like one agent has 1 and the other agent has 0, because we saw that in extreme partnerships where one agent has all the property rights, there is no BIC efficient budget balance and interim individually rational mechanism. Okay, so the real tension there is in fact the property rights. Okay, so the incentive, efficiency, and budget balance are perfectly aligned in that model. Okay. Okay, let me keep going. So, of course, many economists, would say that, well, that's a very, very prior heavy resolution of the problem. So let's try to see if there, if there is such an impossibility, let's try to weaken some of these uh, conditions that we have imposed or constraints we have imposed on the mechanism and see how much we can improve. Okay. So possible resolutions are basically, you can classify them into three approaches. One is to basically say that, we won't insist on efficiency. Okay? We'll relax efficiency. Okay? Second is we will relax budget balance. Maybe it's possible to generate money. The buyer's payment to the seller is more than what the seller needs, and that extra money may be burnt away. Okay, so maybe money burning is possible. Okay, so relax budget balance. Maybe relax the solution concept. So this, we have already seen that relaxing the solution concept from dominance to Bayesian allows for possibilities, but I'll comment more on that towards the end of this lecture. But first, I want to show you some examples to show that the first two approaches give you some kind of a satisfactory resolution to this impossibility. Okay, so first we are going to look at relaxing efficiency. So the precise question is, we are not going to impose efficiency. So we are going to ask the following question: what is the best, quote unquote, best DSIC and budget balance mechanism, where best means the mechanism which maximizes the sum of payoffs or the ex ante expected sum of payoffs of all the agents. Okay, if we have some formulation of these best mechanisms. So basically, it's in a sense a formulation which captures the idea that give as much as possible to all the agents. Okay, so what is a mechanism which is DSIC and budget balance and still redistributes as much as possible? Okay, so that's I'm being vague here by what I mean by as much as possible, but you'll see from the example what I mean. Okay, so in general, whatever way I define this optimization exercise, it turns out to be an extremely difficult problem to solve. Like amongst the class of DSIC and budget balance mechanism, which is the best? We know that such a mechanism cannot be efficient because of the Green-Lafont impossibility. But what is the best we can do? So in an N-agent framework, we had already shown that something like a Green-Lafont mechanism does very well. So the Green-Lafont mechanism, if you remember, so does anyone remember what the Green-Lafont mechanism was? What was it? How was
Yes,
it?
sir.
Yeah, go ahead. Tell me how.
So the
Yeah.
highest valued agent will get the object with probability 1 minus 1 by n.
Yeah, but what was the implementation of that exactly?
So pick some agent arbitrarily or random and then do a weekly auction among n agents, the remaining n agents.
Remaining n minus 1 agent.
If there are total n plus 1 agents, so
Okay,
pick
okay, yeah.
then do a auction among n agents, and then whatever is the value of among those agents, so distribute it to agent chosen randomly.
Whatever the payment generated amongst in the Victory auction, you give it to this agent that you have picked at random.
Yes, sir.
Okay, so that's why this the agent that you pick at random is called a residual claimant. So he just picks up whatever residue is remaining, basically. Okay, so this residual claimant, and the crucial thing here is that the residual claimant is picked with probability 1 over n. So that ensures that the mechanism allocates the object to the highest valued agent with probability 1 minus 1 over n, and to the second highest valued agent with probability 1 over n. The advantage of that is that such a mechanism is asymptotically efficient. With large number of agents, it will allocate the object asymptotically efficiently, and by definition it is a DSIC and budget balance mechanism. So we have a mechanism which is going to approach DSIC efficiency and budget balance in an asymptotic way. So the mechanism, it's defined for n agent. So in an n agent problem, what the Green-Lafont mechanism is saying is that although there is an impossibility like this, there is an asymptotic way of overcoming that by relaxing efficiency. Okay, so this is one way of relaxing efficiency. You can think of other ways of relaxing efficiency also. So, for instance, in this mechanism, the second highest valued agent is given the object with some probability, right? I think when we talked about single object allocation, those characterizations, I discussed another mechanism where the uh, where the object is always given to the highest valued agent, okay, and nothing is given to the second highest valued agent. So I discussed such a mechanism. You can go back and check the notes, and basically those mechanisms also, what you do. So here the entire object is allocated, but there I was not allocating some of the object, but allocating whatever I was allocating only to the highest valued agent. But I was able to do that in a incentive compatible and budget balanced manner still. And so the main difference between that and this mechanism is that mechanism we were wasting some of the objects. Here we are not wasting anything and giving it to a lower ranked agent. Okay, but still both the mechanisms will asymptotically be efficient. So the point of this discussion is that there might be many ways to relax efficiency. This is not the only way to relax efficiency. So there might be many candidate mechanisms which might be asymptotically efficient. Okay, so Green-Lafont mechanism is not the only way to go about it. There are many ways, and figuring out which is kind of the quote unquote best is kind of a very challenging problem. It's not clear which is the best and what is the criteria in which one is better than the other and so on. So these are still unanswered questions till now. The other possibility is to relax budget balance. So what we can do is we can continue to have efficiency DSIC, but relax budget balance. So instead of requiring budget balance, we just require that we can raise money, but we don't require money at any profile. So in that case, you can again ask like, what is the best mechanism, which is DSIC, efficient, and which only burns money but need not be budget balanced. Okay. Well, first, because it's a de-Size efficient mechanism, it has to belong to the Groves class of mechanism. Okay. And basically, so we are searching inside the class of Groves mechanisms, which is kind of the best mechanism, uh, right? Which never runs into deficit. So it will only burn money, but never runs into deficit. Again, it's a difficult problem to solve, but there are mechanisms that you can think of which will burn money, but asymptotically as the number of agents grow, it will achieve asymptotic budget balance. Okay, so I have given one such mechanism here. It's a pretty simple mechanism, but it was only recently discovered, proposed by a computer scientist named Cavallo. So it's called the Cavallo mechanism. So it's related to one question I got in the last class, that, why can't we just do a victory auction, and basically the one of the agents takes up whatever the revenue is generated. Well, such a mechanism will be manipulable. So basically, we can do a victory auction, but we need to smartly redistribute the revenue that we generate in the victory auction. So that's what this Cavallo mechanism does. So the mechanism is as follows. A victory auction is conducted. Okay, so everybody is asked about their type. A victory auction is conducted. The highest agent gets the object, pays the second highest agent's value. Okay, but then the auction doesn't end there. That revenue that we generate is redistributed smartly. So that this is very important, that you redistribute this the second highest value in a smart manner, so that incentive compatibility is maintained. If you design it like everybody gets 1 over n of the second highest value, that is going to be heavily manipulable, right? Because people would then try to jack up the value of the second highest value. Okay, because they will the second highest value bidder would tend to jack up its valuation so that it gets higher return, right? So these things would be manipulable. So here is something that Cavallo proposed, which maintains that incentive compatibility. So take a valuation profile. So to understand the mechanism, take a valuation profile V with V1 greater than equal to V2 greater than equal to Vn. Okay, so let's say the values are like that. Agent 1 is the highest valued agent. So winner, agent 1 is basically makes a payment of V2. Now here is how the redistribution happens. Agents 1 and 2 are given back V3 over N, and others are given V2 over N. Okay. So agents 3 to N are given back V2 over N. Agents 1 and 2 are given V3 over N. If you think about it, here, the manipulation incentives are absent, because the redistribution amount that agents 1 and 2 get do not depend on their valuation. It depends on V3. Okay? And similarly, the redistribution amount V3 to Vn get do not depend on their values, but on V2. Okay? So that means that, they will, so, and of course, the fact that V2 is greater than equal to V3 also will play a role. And so you can formally show that this mechanism is dominant strategy incentive compatible. So agent 1 makes a payment of V2, then is given back V3 over N. Agent 2 also is given back V3 over N. Everybody else gets V2 over N. So the total money collected, the money raised by the mechanism at this valuation profile, well, agent 1 pays V2, but then n minus 2 agents are given back V2 over n. 2 agents are given V3 over n. So these terms are subtracted, and so you get 2 by n times V2 minus V3. So this is the total money collected in this mechanism. Okay. So so notice that this is greater than equal to 0. So that means that if V2 is strictly greater than V3, then basically it will generate some money on the table, but we can't redistribute this in any way. At least this mechanism won't redistribute, and so we burn this money basically. So the agents basically burn this money and or throw it away. Okay, but interestingly, the money collected here approaches 0 as n becomes larger and larger. So what it means is that for large n's, the mechanism will collect very little money. So it will be asymptotically budget balance, and hence asymptotically redistributes all the surplus V1 amongst all the agents. Okay. So is this clear how the Cavallo mechanism works? So you can go back to the to my notes and look at an earlier mechanism that I had discussed in the class, which was similar to this Cavallo mechanism. In that mechanism, what I was doing is, I was doing a Vickrey auction, but not for the entire object, but for some fraction of the object. So basically, if the agent 1 wins, then he is not given the entire object, but given some fraction of the object. Okay, and that fraction was very cleverly chosen, and then the payment generated from that Vickrey auction was redistributed in a similar manner, but that mechanism was budget balanced, and the trick there was to not allocate the entire object but only part of the object. This mechanism is also similar to that, but the main difference is that one was budget balance but inefficient. This one is efficient because it allocates to the highest valued agent the entire object, but it is not budget balanced. So you should go back to that mechanism and try to compare it with this Cavallo mechanism.
Sir, what
Sir,
if there is an authority conducting this redistribution process and demands a basic administration fees, like some minimum threshold?
Who demands it?
The authority conducting this redistribution exercise. So the total payment collected has to be strictly positive, in a sense that it achieves the threshold of that administration expenses.
So in that case, I am afraid that you will again get back some impossibility. That if you have to raise a particular amount at every profile, then you will that may not be possible. So so what you're thinking of is like you impose DSIC efficiency, and you don't impose budget balance, but you impose the fact that at every profile, the mechanism must collect some amount. I think you can rework these kind of arguments and show that something like that would never be possible. That would be an impossibility again.
Okay, sir.
Yeah. Somebody else had a question?
sir, I had a similar question.
Yeah. So all these, the point of these relaxations are just to stay in this model and relax some constraints. If you relax it by, so this the kind of things that you have in mind will basically be kind of equivalent to requiring budget balance, right? So basically, So in fact, if I remember correctly in the notes, there is another example of a public good provision. So basically, so let me spend a little time talking about it. Yeah. So so if you look at the notes, there is another problem that I discussed, which is the public good provision problem. So there is a single public good to be provided. There are n agents who have a value, who have values for that public good. That's the type of the agent, and the uh, the objective is to basically construct a DSIC efficient mechanism. Okay, so basically, efficient mechanism basically says that so there is a cost of providing the public good. So the efficiency says that if the sum of values is greater than the cost, then provide the public good. Otherwise, don't provide the public good. Okay, so there the result that we have is that there is no DSIC efficient in this sense mechanism, which will raise money to cover the cost. So the payment collected should be enough to cover the cost of the project. Okay, so it is similar to what you have in mind, that instead of budget balance, there is this outside party which is conducting this mechanism and it wants some fees. So instead of budget balance, let's say we impose this requirement that the mechanism must collect at least that much fees. Okay, so in that public good provision problem also, we replace budget balance by the requirement that the mechanism must collect at least the cost of the project.
Sir,
Okay,
but that setting is a public good setting, and
but here, but the impossibility is similar. Yeah, I understand it's a public good setting. It's a 0-1 problem, but even then, so basically, even in that problem, you will get into an impossibility result. So in public, private good problems like this, you're more likely to get an impossibility result.
Sir, is the public good result, is it robust to the type of the good that is being allocated? So for example, we have a good which is public, but it also has some private characteristics.
Private
Let's say it's,
characteristics to it.
yeah, so it's partially excludable and not totally
Uh-huh.
excluded
No,
with
no, no,
in
no.
that
So
case.
if it is like an excludable public good, then you may get some possibility results. So there are papers on that. I can direct you to some papers on that.
Okay.
Yeah, it's specific to everyone viewing the good, the object as a good, and so on. Yeah. Okay, so I want to discuss the last resolution to this problem, which is, so we have discussed relaxing efficiency and budget balance. The last one is relaxing solution concept. And this, as I have already told you that, Crampton, Gibbons, Klemperer already have shown that their mechanism works for any, if there are no issues about participation constraint, it is a Bayesian incentive compatible, efficient, and budget balanced mechanism. So without any IR constraint, there is a BIC efficient and budget balance. So we can overcome the impossibility of Green-Law form by using the weaker solution concept of Bayesian incentive compatibility. Okay. So the problem with the Crampton, Gibbons, Klemperer mechanism is that it is only for this single object allocation problem. So there is another mechanism which is called the dAGV mechanism. So dAGV stands for D'Apramo, Arrow, and Gerard Verret. So these are three people. So Claude D'Apramo and the French economist Gerard Verret. So they wrote one paper, and Arrow wrote another paper, both independently, which proposed a new mechanism, which is now known as the dAGV mechanism. it's kind of a Bayesian analog of the VCG mechanism. Okay, so we know about the VCG mechanism, but it's a Bayesian analog of that. So what they show is that their mechanism is very general. It works in any environment. It's just like a VCG. Just like VCG can be applied to any problem, public good, private good with many goods and so on and so forth. dAGV can also be applied in many problems. And they show that the dAGV mechanism is efficient, budget balance, and wage and incentive compatible. So you can think of this as a generalization of Crampton, Gibbons, Klemperer. Okay. So again, notice that there is no mention of individual rationality constraint here, but it works in a more general framework than the Crampton, Gibbons, Klemperer mechanism, which was only tailored for that single object allocation problem. Okay. So what I will discuss now in 15 minutes or so is what is this dAGV mechanism, and we'll argue that it is efficient, budget balance, and Bayesian incentive compatible.
Excuse me, sir.
Yeah.
What is if we have OBIC?
Oh, so OBIC is a solution concept for when types are mechanism is ordinal. So basically, here the mechanism is not ordinal, right? So we are asking for values of agents and so on and so forth. So OBIC is the counterpart of Bayesian incentive compatibility in an ordinal framework where we are doing voting or matching or something like that.
So can we also do this within the ordinal framework, like with preferences? I mean, classical preferences and all that.
Yeah, but what do you mean ordinal framework?
Like instead of asking values, we ask for preferences of agents in something.
So essentially, okay, so I don't want to get into the details of this, but basically the idea here is that our outcome space, right? So the outcome space here is basically the set of all possible payments and the set of alternatives A, basically, right? So there are two components to the outcome, A and this continuum of transfers, right? So we have preferences over that, and basically, so because of the restrictions on the preferences of on those spaces, we have quasi-linear utility, and that quasi-linear utility by definition is a very cardinal idea, right? Because it's equivalent to representing it using BI and so on and so forth. And so for instance, in this model, this BI is on the RA. So if is only required preferences over ordinal preferences over A and not cared about these BIs, then we could use something like OBIG, so and of course then the question is how do we treat transfers and all. So basically the introduction of transfers basically means that you cannot use an ordinal mechanism. I mean, we can't call these mechanisms ordinal mechanisms, basically. Okay, so let's keep that discussion, because unless I have access to a board or something, I cannot really explain what I really meant to say. Let's keep that. So all these big kind of ideas are for mechanism design settings where monetary transfers are excluded. Just try to remember. Okay, so what I want to say here is that the Bayesian incentive compatibility criterion is not to is quite permissive if you don't impose individual rationality constraints. Okay, so the dAGV mechanism is one classic example of that. So here I'm setting up this general model. So we are now away from the single object allocation model. We are in a very general models where there is some set of alternatives A, finite set, and agents have value over this sets of alternatives. So these sets of alternatives may contain like bundles of objects, or it may contain many public goods, or so on. So it can be anything. Okay, so agents have value over that, and that's the private information. That's the type. Okay, and let script vi be the type space of agent, and script v is the set of type profiles. So we are not going to assume anything about the richness of this type space. So it may be a discrete type space, a finite type space, or it may be a continuum type space. It will not matter, okay, for our result at least. All we will assume is that types are drawn independently. So this will be a crucial assumption, that each agent is going to draw the types independently. It need not be identically, but at least each agent should draw their types independently. So this will be an assumption, and this assumption will ensure that the mechanism is Bayesian incentive compatible. With correlated types, the incentive compatibility will become an issue. Okay, so we are going to describe the mechanism. So the mechanism is efficient. So which means that the allocation rule will choose an alternative which maximizes the sum of values at every type profile. So chooses one of the alternatives which maximizes the sum of values of the agents. Okay, so that's what QE does, efficiency. And the payments are constructed using the following key idea. Okay, so the dAGV idea is this. What do I call? I think I call this a residual utility. Okay, so what is a residual utility, or what is the, in fact, the right way to think about is what is the expected externality of agent I with type vi on others. Okay, so that's what this Ri function is. Remember, if you forget about this EV minus I, this is exactly the term that we had, in the Groves mechanism. So the Groves mechanism, it's HIV minus I minus this particular term, right? So which is the value realized by all the agents except agent I in the mechanisms. So that term was there. So here RIVI is just the expected value realized by all the agents except agent I when agent I has value VI. Okay, so I'm agent I have value VI. So I'm going to compute the expected value generated by all the other agents when I report VI. Okay, right? So this is that particular term, RIVI. Okay, so you will see that it's very critical that this expectation is conducted with respect to the true type. The conditioning is done with respect to the true type VI. Okay, so so in other words, it will matter that this this expectation does not depend on what VI is. Okay, so as we go through the proof, it will become clearer, and so that's where the independence will come handy. Okay, so the independence of V minus I with respect to what VI is going to play a role, because this expectation can be carried over, can be carried without knowing the true value of VI. Of course, this term depends on VI, okay, but the expectation should be carried out with respect to the without required conditioning on VI. So that's going to be important. Anyway, don't worry if you don't understand this comment, but just try to remember what this RIVI is. Okay. So just to give you an example, suppose the problem, this is very generally defined. Suppose we just look at single object allocation, and values are drawn from 0 to beta for all the n agents. So identically drawn, let's say. So the efficient allocation is highest agent gets the object. So what is RIVI? Well, we know that other agents get some value in the single object allocation problem if agent I does not win the object. So if agent I does not win the object, then somebody else will win the object, okay, because the rule is efficient. And when does agent I doesn't win the object? Well, whenever VI is not the highest, right? So whenever the max of V minus I is greater than VI, this term is positive, otherwise it is 0, right? So basically, others get value when agent I is not the winner. So then the value is basically max of J not equal to IVJ. Okay, so this term, this summation is basically max of J not equal to V. Okay, so this expectation is basically the expectation of maximum of n minus 1 random draws, condition on the fact that the maximum is higher than VI. Right, so that's what that's what this term will look like.
The interpretation of RIVI is not so clear.
So interpretation is that it's a very simple interpretation that what is the expected value others are getting when you have type VI. So this is something that you are computing before participating in the mechanism. So you don't know what the V minus I's are. So that's why you're computing the expected value V minus I. And this is an artificial construct. We're going to use this to cleverly construct the payments. Okay. So what is the, so this is like expected welfare of others when her type is VI. That's the RIVI interpretation. So the payment in this dAGV mechanism is the following. An agent I who at type profile V pays an amount which is equal to its own RIVI subtracted by the average of RJVJs of the other agents. So this term, the subtracted term, is the average of RJVJs of the other agents, and RIVI minus that average is the payment of the of agent I. So why is this particular choice of payment? Well, as you can see that if I sum over all the TIVs, you will get this right hand side summing to 0, right? Because this is sum over RIVI, and this summation is a double summation, first summed over J and then summed over I. But this double summation will mean that every Ri will occur at exactly n minus 1 times. So this n minus 1 cancels. So you'll get again sum of RIVIs. So these two terms will cancel as you sum over all TIs. Okay. So essentially what you will get is that the constructed mechanism by definition is budget balanced. Okay. So we have already satisfied efficiency because we are allocating, the object. We are choosing an allocation which maximizes the sum of values. Our payments are chosen in a manner so that it's budget balanced. Okay. So it's kind of an interim analog of the VCG idea that agents pay their kind of expected externality to others. Okay, so this is the expected welfare that agent I thinks that others will get. Okay, when he participates, this is the sum of, or the average of, expected welfare that others are thinking, and so the difference is what you pay. Okay, so what what we will show is that the dAGV mechanism is efficient, budget balance. We have already seen that, so it is Bayesian incentive compatible.
Sir, how this mechanism is exactly different from VCG?
Well, it's different from VCG is because it's not, so there are these expectations being carried out here, right? So the VCG would not have these expectations here, right? Okay.
Basically, it is a Bayesian setting. In that sense, it is different.
So it's this mechanism is going to be Bayesian incentive compatible and not dominant strategy incentive compatible.
Okay, sir.
Okay, and these this term is chosen in a manner such that the sum of TIs is equal to 0. If you did not take this expectation and try to construct something like this, you can never do it. You can never do it because if you remember, the gross mechanism is HIV minus I minus this particular term. So this term has to be completely independent of VI, right? And that's not the case here, right? Because so it'll depend on well, in this case, I take that back. So it is independent of VI because it's only depends on RJVJs and expectations over V minus J. So it'll so if you put exactly this, it will be fine. But then RIVI will not be RIVI because you will not have this expectation. So it won't cancel each other out. But if you write this instead of RJVJs, then it will not be independent of VI because here there is a VI term. Only if you take this expectation, it becomes independent of VI, right? So in that sense, basically, it's so you can, so you should try this exercise that why can't we do this using the gross mechanism. So basically, not take the expectation here, put that term in here, and minus 1 over n minus 1 sum over this over the other agent, and verify that the right term here is no longer independent of VI. Okay, because that's what the gross mechanism requires, right? It's some HI V minus I minus that, right? So it won't actually come like that. Okay, so it won't be a gross mechanism in that sense, even though it is budget balance. So all these things, if you really want to understand, you have to sit down with the notes and get your hands dirty and write it and see what is going wrong. If I just say like this, it may be very unclear, but if you're interested, you should just do these things page by page of my notes and see why it is. Why we can't do this step for a dSIC mechanism. For a dSIC and efficient mechanism, it has to be a gross mechanism. And if we try to write it like this to make it budget balanced, it's no longer a gross mechanism. Okay, so that's the idea. But if you take this expectation, magically you can construct this as a budget balance mechanism. And you can also show that it is Bayesian incentive compatible. Okay. But it's
Sir,
not,
how are the
Yeah, go ahead.
Sir, I was asking how are these constructions arrived at? For example, in CGK, we also saw an elaborate construction of the transfers. I
Yeah.
mean, how do they arrive at these constructions?
How do they arrive? Meaning, I mean, there is, you just have to think like, how can we make this work? I mean, so by looking at, by, I mean, that's the innovation of the paper, right? So they basically thought hard about how this can be possible, and they came with this innovation. So that's why this is a seminal paper, I guess. So, so you need to be able to think that what is it that is required to make it budget balanced. Well, something like that. This is a good candidate because it looks like a budget balance mechanism. Well, the only thing to verify is if it is Bayesian incentive compatible, and so this is pretty natural to guess, right? So in the gross mechanism we had such a term, and so here instead of because it's a Bayesian environment, instead of looking at the welfare of others, you look at expected welfare of others. Well, once you define it, is there a way to construct a budget balance mechanism? Well, this looks like a very good candidate. So RIVI minus this particular term. There may be other ways to do it, but this looks like a candidate. Okay, and hence once you have this, you just need to verify that it is going to be Bayesian incentive compatible. Okay, and so again, there is no systematic way of coming up with these answers. You just need to think about these problems long enough to figure these things out. Okay, so that's why I keep saying, even if I teach these things on Blackboard or on slides here, if you just listen and go home, it's not going to be enough. You just have to work hard. Just have to read the papers that I post on the course webpage. Then only you will get a feel of things. Otherwise, it will be very difficult. Okay, so these are not easy things which have natural intuitions. In many courses there are natural intuitions which work, but in these courses these are theory courses. There is no intuition which will work. You just have to think hard about the problem and read a lot of stuff to gather enough insights. Okay, so I just want to show that this mechanism is Bayesian incentive compatible. So remember, for Bayesian incentive compatibility, what we need to show is that if there is an agent who has type VI, then his expected utility is greater if he reports VI than if he reports VI prime. That's what we need to show. Well, what is the expected utility if he reports VI? Well, this is the value he gets from the mechanism. So this is the alternative that gets chosen, and this is the VI of that alternative. Okay, so this is the efficient allocation rule. Plus, this is the transfer that he receives. Okay, so the expected value of this, where expectation is taken over the types of other agents, is what is the expected utility. Well, first step is we simplify this. Okay, so we know the exact formula of what it is. We have defined it. So we just replace it here. Okay. So you can just forget about the expectation term here. We'll just work with the inside terms here. So I expand this, and then basically, remember, I have to compare it with VI prime. So what I do is I add RI VI prime and subtract RI VI prime. Remember, when I'm computing the same term for when the agent reports VI prime, this term will remain the same, right? Because VI prime will just come here, but this term will remain the same. So that's the idea, that I just add the RI VI prime and subtract RI VI prime. Okay. And then basically I take this term, sorry, I take this term, I take this term, and I take this term and put them together. And then I basically, what is remaining is basically RIVI and minus RIVI prime. So these are the two terms remaining, right? So I've taken everything in here, and these are the two terms that is remaining. So here I just replace what RIVI is, okay? So RIVI is expectation of this, where I use VI here, and RIVI prime is this expectation where I use VI prime here. Okay. So remember this expectation EV minus I, okay, is independent of VI. Okay. So that's why, these two expectations are the same, whether it's VI or VI prime. I'm just expecting out V minus I. So it's the same expectation, the same distribution over V minus I that I'll be using. So this is the place where I'm using independence. Okay. So whether it's VI prime or VI, okay, these two expectations are using the same distribution. Okay. So here I've just expanded RIVI and RIVI prime here, and I get this. And the remainder of the proof is basically, so this I can take it inside. So this whole thing I will take inside here. So then it becomes the sum over all the V, all the agents value. That's what I have here. I keep this term, and so only this term remains. Okay. So this is the only term which is remaining outside. And here I have everything, but this term is there. This is the place where I use efficiency, because this is the efficient one. This is greater than equal to QE VI prime V minus I, the summation over that alternative. So this is where I use efficiency, and these terms remain as it is. Okay. And then I basically aggregate, I disentangle again. So I keep VI and take out everything outside, and basically you will get back this term again. Okay. So essentially if you take out everything again, that one and this one cancels, and you will get this, and this is nothing but this, which is the expected utility of the agent when his true type is VI but reports VI prime, and this is his state. So that's why BIC holds. And so the proof is very, very similar to Grove's mechanism proof, right? So, somehow we, come up with this because of the way the payments are constructed. You can come up with this summation of BI terms, and you use efficiency once, and then you basically disentangle again to get the utility of VI prime. And the expectation operator remains outside all along, and it works. Okay, so that's the proof. So this basically shows that there is a general possibility result with independent types, that Bayesian incentive compatibility, budget balance, and efficiency are compatible always. So this is one way to escape the Green-Lafont impossibility result in very general models. Okay, but the main issue is participation constraint. So these dAGV mechanisms, they may give negative interim payoffs to agents even in a simple bilateral trading model. So you can just set up a simple bilateral trading model, and take uniform distribution and try to figure out the payments at certain types and so on. Okay, so think of the following bilateral trading model. The buyer and the seller draw their value from 0, 1 uniformly at random. Okay, so uniform distribution 0, 1. Okay, and so what is the dAGV mechanism in that case? Okay, can you write down the payment formula for dAGV mechanism? You need to compute this, because it's all uniform. You can try to compute the terms, and basically you'll have an expression and you will see that the payments are budget balanced. It's an efficient mechanism. It's Bayesian incentive compatible, but you'll see that at some profiles, okay, or even in an interim sense, some types of the seller will have negative utility, or some types of the buyer will have negative utility. Okay, so the participation constraints will be violated. Okay, so this is you can do this as an exercise. That the dAGV mechanism may give negative interim payoffs to agents, even in a simple bilateral trading problem. Okay, so that's where the kind of more interesting questions start occurring. That uh, the dAGV mechanism doesn't satisfy interim individual rationality. So what is the best mechanism, quote unquote best mechanism? Okay, so we can satisfy BIC, budget balance and efficiency, but then what's the, can we relax some of it and satisfy interim individual rationality? What is the best mechanism to do it, and so on? So those are very hard questions. There hasn't been any satisfactory resolution to these kind of questions. Okay, so I'll stop here. Are there any questions? Okay, so what I will suggest you is like over 1 week or 10 days, you take time to read this part of the course. So when I say this part, like from the Groves mechanism onwards, so from the time we introduce transfers, so those notes till these redistribution mechanisms, you try to read everything, collect your doubts, or collect the parts that you had understanding problems, and we can discuss about it in one or multiple sessions. But I will request you to aggregate those doubts or revisions or so on, and send it to me by email so that I know what I need to go over and I can go over those things. Okay, so let's set a deadline of, let's say, so today is 20th, right? So let's say by 27th, if you can, let me know your doubts. Then in that week, the 27th week, we can have a revision lecture, doubt clearing revision lecture. Okay, is that clear?
Yes, sir. Okay. Okay, sir.
And the other thing is, for the redistribution mechanisms, I don't have any, assignments or anything, but there is a very interesting paper by Claudio Mazzetti and Makowski. So it's on this, one seller, many buyer problem, but in a slightly different model. So we saw that for the one seller many buyer model, the Crampton Gibbon Klemperer result does not apply. I mean, they show that you can't dissolve such partnerships. So in this paper, they show that you can dissolve even those partnerships, but the distributions have to be asymmetric. So the seller distribution has to be different than the buyer distribution. If you allow for asymmetry, then you can dissolve even those partnerships. That's what they show in that paper. So it's an interesting paper. You should read it carefully to get an idea of what is driving that result, and write a referee report that you did earlier for other papers and send it to me by 27th again. Okay. Okay, any other questions?
Sir,
Yeah.
have you and the other teachers decided something about how the exams will be conducted and when they will be?
No, I haven't yet. So most likely, it will be, I mean, I will let you know, but Most likely it will be something, via Zoom or something.
Okay.
Okay, and we won't delay it also, so it will be most likely before the 10th of May or 15th of May. We'll decide it soon. No problem.
Okay, sir. Okay.
I mean, at least for me, I don't know about other teachers.
Okay, sir. Okay.
Any
So, the public good redistribution which we were talking about.
Yeah.
So the result there is that the unique mechanism.
So I said that there is no mechanism.
Yeah. So in that mechanism, the cost cannot be covered, right? So is that the only DSIC and whatever all the property? Is that the only mechanism?
No. Did I talk about any mechanism? I said that if you require from a mechanism dominant strategy incentive compatibility and the fact that you only provide the public good when the sum of values is greater than the cost. Okay, so this is what I'm calling efficiency here. So if you require from any mechanism DSIC efficiency and the third property, which is that the sum of payments collected is greater than equal to the cost. Okay, there is no such mechanism. Okay, such a mechanism cannot exist.
So notes there is a mechanism where the sum of values is greater than the cost, but the sum of payments is not, and it's we basically use the pivotal mechanism there.
Yeah, but then it will not cover the cost, right?
Yeah, that's right.
So you can use pivotal mechanism or any variant of a gross mechanism. There might be other variants of gross mechanisms which can also work, but all those mechanisms will fail to cover the cost. Yeah. So then you can ask a further question. Then what is the best mechanism in that class? Okay. So in the sense that which minimizes the amount of deficit that you want, you can have. Okay, so as I said, keep reading the notes and keep collecting doubts and requests for revision, and I'll be happy to have more than one class to cover this. Okay.
Sir, one thing you said that the exam will be conducted through Zoom. So
Yeah.
I didn't quite understand how through Zoom.
We'll discuss the logistics when we.
Okay, sir. Okay.
Okay. Yeah. Bye.
Bye, sir. Thank you.
Bye, sir.